So we're moving on to the second part of chapter 32. And so let's start right away with a question. We know a little bit about how the magnetic field from a wire works. So taking our knowledge of this, suppose we take a wire and make it into a loop, like in this picture here. What direction would the magnetic field be at point A? So use your right-hand rule, see what you come up with, and we'll talk about this. Okay, so the answer I get is it'll be pointing out of the page. So let's take a look at this. So here's our loop. Now we take our curly right hand rule. If I look at the bottom and I put my thumb along with the current from the bottom, okay, in the middle of the square, my fingers are pointing out of the page, and then they'll be pointing into the page on the other side. All right, if I look at the right side, I see the same thing. Okay, into the page, out of the page. The left side, I get the same thing, and then finally the top, I get the same thing. So you see that the wire has a tendency for the field to be coming out of the page in the case where it is here, where it's going counterclockwise. So where the current is going counterclockwise, the magnetic field is coming out of the page. So hopefully that's what you got. Points out of the loop, and we can use our curly right hand rule to figure this out. And so here's a picture of a loop. So generally when they have loops, they'll make them little circular loops. And if you look at these two loops, it's the same sort of idea. Okay, so if on the right-hand picture, the loop, the current is going counterclockwise, and inside the loop, the magnetic field is coming out of it. All right, and if you look, there's a side picture, it's the same sort of idea. You can use your right-hand rule to get that association. So we're going to deal with these loops. And here's the right-hand rule for dealing with loops. So the first one is basically doing the way we just did it. So you point your thumb in the direction of the current, and then see which way your fingers point through the loop. And that's totally fine. If that makes sense to you, do it that way. Another way to think about it that can be a little bit quicker is sort of switching up your fingers and your thumb. And so curl the fingers of your right hand around the loop, and then your thumb is pointing in the direction of the B field. So if we go back to that loop we were doing, if I take my fingers and make them go in a counterclockwise direction, my thumb points out of the page, out of the screen, and that's exactly which way the B field points. If I look at this loop here on the right, if I put my fingers in the direction of the loop, my thumb points out of the page. I usually generally do this way. It's another right-hand rule to remember, but I think it's a little bit easier. And so here's a picture of a current loop and comparing it with a permanent magnet. And actually the lines look pretty similar. Okay, so what we do is we actually will call the North Pole this side over here, and the South Pole this side over here. All right, and so when I do this with my right hand rule, my thumb is sort of pointing where the North Pole is. And so here's an example for you guys to give it a try. So here we have a little loop. It's coming out of the page on the right and going into the page on the left. The current is. I want to know is which side of the current loop is the North Pole of this little magnet. So give us a try and let's tell us what you think. All right, so hopefully you got that it's the bottom side. So if I do my right hand rule again, if I put my fingers in the direction of the current, which is coming out of the page and going into the page, my hand is sort of situated so my thumb points down. And so in this picture here, the north side of this magnet would be here and the south side would be here. So you really want to stress this idea that when you have a current loop, it's like you have a little tiny permanent magnet. Okay, so currents and magnets produce a lot of the same results. Here's another example, kind of doing the opposite. Here we have the magnetic field lines. I want to know is what direction do you think the current would be in this loop, and then which side would the North Pole be? So give this a try and let's see what you think. Okay, so here I get this answer. So if I put I'm using the second right hand rule. I put my thumb in the direction of the magnetic field line so it's pointing down. My fingers tend to go counterclockwise around this loop. All right, and because of that, where my thumb is on the down side, the bottom side, so that's where the north would be. So again, the north would be down here at the bottom side of this, over here, and the south would be over here. This is really tricky, especially in a video. Give these a try and see what you come up with, and of course we'll do over some more examples in class. Here's another little picture of the same setup. They like to show these little pictures in the book, like on the right, where they have little iron fillings, and basically those are like little compass needles, and they line up with the magnetic field around it. So it's kind of showing you that it really is, the magnetic field really does look like that. One last comment about these loops. So you can call a loop of wire like this, we call this a magnetic dipole. And so we dealt with this before when we did electric dipole. An electric dipole was a positive and a negative hanging out together. Well, now if you have a wire loop, okay, like so, and suppose this is the north side and this is the south side, that's what you have. You have the north and the south. It's very analogous to having plus and minus. Okay, and so we call this the dipole. This will come up again. We won't deal with it too much right now, but one important definition is there's a definition of the magnetic dipole. And it's simply the area of the loop, so whatever the area would be here, so you find the area of that, this would be pi r squared or something, times the current in the loop. All right, and then the vector points from the south pole to the north pole. So in this case here, if I take my fingers around with the current, my thumb would be pointing upwards. And so this would be kind of my north side, this would be my south side, and so the direction of it would be pointing this way. In this picture, the direction would again be pointing this way. Okay, that's a definition, and we'll pick up this definition again later at some point. Now we're going to move to what's called Ampere's law, and this is definitely a little bit tricky to get into, but it's a pretty powerful law, so we want to talk about this. And so the first thing we're going to talk about is what's called line integrals. And a line integral, literally all that is you're just adding up little tiny segments. So here we have a line that goes from I to F. All right, what we do is we break it up into little segments. Each segment is a distance delta S. All right, and if I wanted to figure out the total length of this line, I would do something like this. I would sum up, okay, the distance delta sk over every element of that. So basically sum up all those little delta s's, and that would give me the length of that line. Now if we want to get this to be more and more precise, basically you take this delta sk and make it smaller and smaller to the limit that it goes to 0. This becomes an integral, right? If we remember, all integrals are really just sums. That's a nice way to think about integrals when you're trying to think about, at least conceptually, how to do this. Now, the thing we're going to be dealing with here, is going to be a line integral that looks like this here. Okay, and so it's a little bit mathy, but I'm going to try to go through and explain what's going on here. So this is the line integral. First of all, there's a little closed circle here, and that means that closed circle means that you're going to do this in a loop. Okay, so when you go around and do this line integral, you're going to be basically going on a permanent loop and coming back to where you started from. This stuff in here is called the dot product, and it's the B field dotted with delta S. And basically, if we have our sort of line segment, so here's some line segment, okay, if there's some point, okay, you can have a B field, and then this delta S is just the little segment of distance that we were talking about before over here. And so at any point, there's basically an angle between the B field and the delta S. And what this thing wants us to do is basically take B field times this distance delta S times cosine of the angle. So what this actually breaks down to is that it's B times cosine of the angle times ds. All right, so this is the same thing as this guy here. And this is basically what we're always going to use. And furthermore, we're always going to do cases where both the B field and the cosine are constant. When that's the case, I can pull that piece outside like so. Okay? Whenever something is constant, you can always pull it outside of the integral. And so here I have the integral of ds, and that's always just going to be the length of whatever the heck you're talking about. Okay, so every time that we ever might use this, okay, this horrible, ugly looking thing over here, all right, is just going to break down to this right here. It's going to be the B field times cosine of the angle and then times the length of the actual line that we're talking about. So this Ampere's law is really only useful in cases where it works like this. Otherwise, if the B field isn't constant, this thing is really nasty and it's not really fun to do. And so here's the breakdown of this. So it's even kind of simpler than that. There's literally two cases. Okay, there's one case where here the B field is 90 degrees to the line. Okay, so if this is our ds, this would be our line, that'd be the B field. If it's 90 degrees, okay, our function, we said it was B cosine times the length. If the angle is 90, cosine of 90 is 0. So if it's 90 degrees to the line, it's 0. And then the other case will be over here when it's 0 degrees. So here the B field and the ds are 0 degrees off of each other. And in that case, our B times cosine of L, the cosine would be 1. So this would be 1. It would just be B times L. And so those are literally the two cases that you'll actually have to do this. Okay, and it breaks down to like that. Again, if you have questions, please let me know, and we can talk about this in more detail. And so here's how we can use Ampere's law, and we'll do an example that we already know about. Okay, so here I'll just sort of say, here's a current carrying wire, all right, and I know that the B field kind of circles around. All right, we know from our right-hand rule that the B field circles around this way here, and at any points, I'll call this R, from the current carrying wire, it's constant. And so I'm going to make this position here to be the loop that I'm using. Okay, and we'll actually, sometimes the book will call this the Amperian loop. So this is my loop, and so I'm going to do this B dot ds business. Okay, now we know that the B field is constant here, and the B field is tangent to the circle. So this is going to be the case where the B field is going to be, or this quantity here will just equal B times L. Okay, and what is that L? Well, in this case, the L is just the circumference. So it's B, and the circumference for a circle is just 2 pi r. Okay, and so we take this and this relationship here, and what we realize is something interesting, is that if you remember, the actual equation that Knight calculated here looks like this here. Okay, this is the actual equation we calculated and talked about on Wednesday. And so if we were to put in these two pieces over here, then when I solve for the B field, I get exactly what I'm looking for. And so what we've done is we've kind of proven to ourselves this idea of Ampere's law, which is just that this here is Ampere's law. So the left-hand side is this line integral business, and the right-hand side is that old constant of ours times the current enclosed. Okay, so in this case here, it's basically how much current is enclosed by the loop that you make over here. Okay, and for us, it was just the current of the wire, which was I. All right, and so this is Ampere's law. It says that this looking thing here, this ugly looking thing, equals U naught times the current enclosed. And basically, it gives you a way to solve for the B field in kind of a fast manner. If you remember the way that Knight did this, it was really ugly and used integrals. We did it here in just a couple of lines, okay, although it is a pretty intense couple of lines. So here's the definition, the fundamental definition of Ampere's law, and they're kind of talking about the same way I did. They used this example of a current carrying wire and how you can sort of show that that's what Ampere's law should look like. And so here's just a little sort of, we were talking a little bit about the left-hand side. The right-hand side is literally just you look at how much current is going in through that loop. So in the example here, there was a current I2 going this way, a current I3 going that way, and a current I4 going that way. And so basically what you do here is you pick sort of one side to be the positive direction. Okay, and so for the total current enclosed in this case, let's see, so the total current enclosed in this case, I would say it was I2 plus I4 minus I3. And that's how you calculate the current enclosed. And so here's a give it a try example. So here we have our Amperian loop, and the line integral of B around the loop is said to be U naught times 7 amps. And so I want to know, what does current I3 have to be in order for this to be correct? Give this a try and see what you think. Okay, so I got that it has to be 1 amp into the screen. All right, and so what we're saying here is we're saying that that line integral thing, the B dot ds business, they're saying that that for us equals U naught times 7 amps. Well, we know that this has to equal U naught times the current enclosed. And so the current enclosed by our loop, enclosed, has to be 7 amps. And so if you look at the picture, there's 8 amps here in the positive direction coming out. The reason we know that it's positive is because if you put your hands and your fingers along with the current of the Amperian loop, your thumb points out of the screen. And so that sort of defines which way the positive direction is. All right, so now the current there is 8, and so what has to happen is the current of I3 has to be equal to 1 amp, and it has to go inwards, so that when you add up your current enclosed, okay, it's that 8 amps minus 1 amps, and that gives us 7 amps. Okay, so that's how that current enclosed business works. And now we're going to use Ampere's law to try to understand something that's pretty important, which is what's called a solenoid. And a solenoid, so we learned a little bit before that if you have one loop of wire, okay, one loop of wire, it makes a magnetic field. Well, a solenoid is basically a bunch of loops of wire combined to make a much stronger magnetic field. All right, and the way that it works is here's a little picture with the iron fillings. Okay, it makes a very strong magnetic field through the center of the solenoid. And here's a picture of a solenoid and a bar magnet, and you look at the lines, they're very similar. So a solenoid is extremely similar to a bar magnet, except that we control it because we control the current going through it, and so we can control how big the magnetic field is. Bar magnets are very tricky to control, and they're just about as strong as they can be. It's much easier for us to control a current. And so in most applications, if you need a magnet, you're usually going to use something like a solenoid, okay, to make this work. And if you look at the picture here, the right-hand rule works in a similar fashion. If you look at the loops, the current is coming up. If you look at the current on the right side, it's kind of coming up, and it loops around. And if you do your right-hand rule, you should be pointing to the right for the north end of that solenoid. Here's another picture of the solenoid. Again, this is very similar to a bar magnet, and it's the basic electromagnet. And so the current here is going through these black loops. It's going sort of down. And so if you try to get your right-hand rule and convince yourself that if that's happening, that the magnetic field, the north part, moves to the right. And again, we'll talk more about this. It's tough in a video. So one thing I want to show you is how you can calculate, so we're not just giving you some random equation here, how you can calculate this for a solenoid. And so for a solenoid, I'm going to draw the picture kind of like this. So a solenoid is a bunch of current loops, like so. Okay, so the field's coming out here and going in over here, for instance. If I make my Amperian loop like so, okay, the magnetic field is going to be pointing this way, and it's only going to be acting on the bottom part of my loop. The B field everywhere else, okay, we're going to say is basically 0, because for a solenoid, the B field anywhere else is pretty weak. And so if I do my Amperian loop, okay, I get this B dot ds equals U naught times the current enclosed. Now remember, the B dot ds, that's just the B field times the length whenever it's 0 degrees. And so right through here, it's 0 degrees between the loop and the B field. And so if I call this loop to have a length of L, this will be B times L on this side. And then over here, it's U naught, and it's basically just the number of loops that I enclose times the current. So here it happened to be 1, 2, 3, 4 loops, but it'll depend on your particular situation. And so if we solve this, we get this equation kind of like here for the solenoid. And we usually define lowercase n to be this special thing, which is the total number of loops divided by the length of the solenoid. And so here's a way to solve this using this Ampere's law. We'll talk much more about this in class. This is really tricky to get your head around, but we'll talk more about it. But the important thing is that we'll never ask you to actually calculate something like this. And the result here is that we get this for the magnitude of a solenoid. And the important thing is this little lowercase n is basically the number of turns of wire per meter. Okay, and so in your problem, you'll be given enough information to calculate that. And so, for instance, here I had a solenoid with 8 turns that was 5 centimeters long. Here's how I calculate that little n. And then otherwise, to get the answer, it's just the U0 and the current. And then finally, just example of a solenoid would be an MRI machine. Okay, any large magnet that we use is generally going to be a solenoid.